Posse-wid, the purpose of a system is what it does. We usually define an organization by its mission statement or its official org chart, but if a company claims to prioritize innovation while consistently shipping delayed products, its mechanical purpose, its true function, is the production of those delays. This principle was established by Stafford Beer, the British pioneer of management cybernetics, as a tool to strip away corporate illusions and identify the actual behavior of a system. Beer's work in management cybernetics suggests that fixing a failing enterprise requires observing its systemic outputs rather than tweaking its intended reporting lines. When a system's purpose is defined strictly by what it does, a stagnant corporate hierarchy is functioning exactly as intended. Its structure is optimized to produce that stagnation. To understand why these structures fail under pressure, we have to look at Ashby's law of requisite variety. In cybernetics, variety is a measure of complexity, the total number of possible states a system can occupy. Every business faces external variety. This is the complexity of the market, driven by shifting consumer demands, technological shifts, and global supply chains. To remain stable, an organization must generate its own internal variety. It needs the regulatory capacity to process information and execute decisions that match the complexity of its environment. Traditional top-down hierarchies struggle with Ashby's law because they restrict information flow. As shown here, when market data is forced through narrow managerial bottlenecks, senior leadership becomes decoupled from operational reality. Long-term survival depends on an architecture that distributes complexity throughout the organization instead of attempting to suppress it from the top. The viable system model provides that architecture. It is a blueprint designed to map the necessary flows of information rather than static lines of authority. The foundation is System 1. These autonomous units do the primary work of the organization: product teams, clinics, or manufacturing plants. Sitting at the edge, they require high levels of local autonomy to process environmental variety as it occurs. To keep independent units from colliding, the model introduces System 2. This coordination function uses shared standards, schedules, and common languages to prevent different parts of the system from oscillating out of sync. In a modern enterprise, an AI backplane automates this coordination. By managing dependencies, shared resources, and event-driven architectures in real time, it removes the need for manual managerial intervention. Coordination at scale is achieved by algorithmically removing friction between autonomous units rather than imposing top-down control. System 3 handles the here and now. This control function allocates resources and optimizes current operations across all System 1 units to create synergy. However, System 3 risks becoming disconnected if it relies solely on filtered status updates. The model solves this with System 3 star, the reality audit. This direct, unfiltered channel into the operational layer verifies the truth by bypassing standard reporting lines. An AI backplane makes this audit continuous. Monitoring telemetry and live KPIs directly from the operational layer, the system provides an accurate picture of reality, replacing the need for manual monthly reviews. Effective systemic control is only possible with real-time data. Relying on curated reports creates a gap in variety that eventually leads to failure. While System 3 manages the present, System 4 looks forward. Acting as an intelligence eye, it focuses on the future environment and emerging competitors. This creates a negotiation loop. System 3 seeks efficiency for today, while System 4 identifies adaptations for tomorrow. Predictive AI serves as a high-capacity System 4, running simulations across vast datasets to provide options for future adaptation. System 5 sits at the top. This policy function defines organizational identity and resolves the tensions between present execution and future planning. In this framework, senior leadership avoids micromanaging operations. Their specific function is to maintain identity and arbitrate the balance between current performance and future survival. Even a well-balanced system can be overwhelmed. Standard communication channels are often too slow to handle a sudden existential crisis or a massive environmental shock. The model accounts for this with the algorithmic signal, a pain or pleasure alert that bypasses the entire hierarchy to notify System 5 immediately. These signals fire only when critical viability thresholds are breached, alerting senior management to major anomalies without burying them in noise. AI anomaly detection triggers these signals. By identifying deviations in operational data as they happen, the system prevents fatal delays in executive awareness. An organization without an automated emergency bypass is poorly equipped to survive sudden, catastrophic change. These principles operate through recursion, the idea that every viable system is composed of and contained within other viable systems. The organization is structured like a fractal, repeating the same essential pattern of 5 subsystems at every scale. A single product team, the broader business unit, and the global enterprise each require their own system 1 through 5 to remain viable. This recursive structure ensures that complexity is processed at the level where it occurs. By resolving issues locally, the organization prevents information from pooling into executive bottlenecks. The VSM provides a scalable geometry of viability, allowing organizations to process complexity at any scale. When Stafford Beer developed these models in the 1970s, their implementation was limited by human processing bandwidth and the difficulty of manual data routing. Modern organizational design has moved beyond drawing lines of authority. It is now an exercise in engineering high-volume, automated information flows. Artificial intelligence and event-driven architectures provide the technological infrastructure needed to power this model in a modern business context. Today, the AI backplane seamlessly integrates daily operations, system coordination, and predictive intelligence into a single synchronized network. Organizations that engineer automated networks of viability are better equipped to navigate modern complexity than those relying on manual hierarchies of authority.